All right, today we're going to jump into two super powerful ideas from math that help us describe the physical world, divergence and curl. Now, I know they might sound complicated, but they're actually a beautiful, intuitive way to understand the invisible forces that shape, well, everything. So let's dive in and learn the language of flow.
I mean, think about it for a second. How do you actually picture something like the wind, or the pull of gravity, or a magnetic field? You can't see the force itself, right? You only see what it does. So how on earth do we draw a map of these invisible forces and flows?
Well, the answer is this really elegant concept called a vector field. The idea is simple. We assign a little arrow, a vector, to every single point in space. That arrow tells us the direction and the strength of the force at that exact spot. Now, to keep things manageable for this explainer, we're just going to focus on two-dimensional fields that don't change over time.
Okay, to really get a gut feeling for what these fields are all about, we're going to use this amazing mental model. We're going to imagine that every single vector field, no matter what it actually is describing the flow of some kind of fluid.
This idea right here is the absolute key to everything we're about to talk about. Even if we're dealing with something totally abstract like gravity, just asking, what would this look like if it were water, unlocks so much intuition. And that's exactly how we're going to tackle divergence and curl.
So let's start with our first big concept, divergence. When we're picturing our vector field as a fluid, divergence tells us something really specific about what that fluid is doing at any given point.
This slide just nails the core idea. If a point has positive divergence, it's like the fluid is just appearing out of nowhere and flowing outward. Think of it like a faucet or a spring. We call that a source. And if a point has negative divergence, the fluid is flowing inward and disappearing, just like it's going down a drain. We call that a sink.
So the takeaway is pretty simple. Divergence is just a number we calculate for any point, and that number tells us if that point is acting like a source or a sink. Positive number, it's a source. Negative number, it's a sink.
Now, why is the number 0 on this slide so important? Well, for a real physical fluid that you can't compress, like water, the divergence has to be 0 everywhere. Think about it. Water can't just pop into existence or vanish into nothing. And that simple fact that the divergence is 0 becomes this incredibly powerful rule in real-world physics.
Okay, so divergence is all about fluid flowing in or out. But what if the fluid is spinning? Well, that brings us to our second key concept, curl. And this is the beautifully simple question that gets right to the heart of what curl is. Just imagine you drop a tiny little twig or a leaf into our imaginary fluid. Does it just get carried along, or does it start to rotate? That tendency to cause rotation, that's what we call curl.
So if our little imaginary twig starts to spin clockwise, we say that point in the field has positive curl. It's just a mathematical convention, really, but it gives us a number to measure the local rotational vibe of the flow right at that spot.
And as you've probably already guessed, if that twig starts spinning the other way, counterclockwise, we say the field has negative curl at that point. Simple as that. Clockwise is positive, counterclockwise is negative.
But here's where it gets really cool. A field can have curl even if the fluid isn't obviously moving in a circle. In this example, the flow is just moving straight, but it's moving faster at the top than it is at the bottom. That difference in speed pushes the top of the twig harder than the bottom, which makes it spin. It shows that curl is about the net rotational effect, not just perfect circles.
So, okay, we have sources, sinks, and spins. Why does any of this matter? Well, this isn't just some clever analogy we made up. This is the actual language used to describe some of the most fundamental laws of the entire universe.
And this is the big payoff. The four equations that are the bedrock of how we understand all of electricity, all of magnetism, and even light itself, Maxwell's equations. They are written entirely in the language of divergence and curl. It's the native tongue of electromagnetism.
Let's just break this down for a sec. The divergence of an electric field, that tells you where the electric charges are. Positive charges are the sources, and negative charges are the sinks. But the divergence of a magnetic field is always 0. That's a profound way of saying there are no magnetic charges, no single north or south poles by themselves. And then you have curl, which describes this incredible dance where a changing magnetic field creates a rotational curl in the electric field, and that changing electric field creates a curl back in the magnetic field. And that dynamic interplay, that constant back and forth caused by the curl of these two fields, that is literally what light is, an electromagnetic wave propagating through space. These mathematical ideas are the very reason light exists. It's just incredible.
And get this language isn't just for physics. You can create a vector field to describe things that aren't even spatial. Think about the population of foxes and rabbits. A vector can show how those populations are changing. Are they heading towards a stable point? Are they caught in a cycle? Divergence and curl help us analyze the dynamics of all kinds of complex systems.
So the really big idea to walk away with is this. Divergence and curl are not just abstract math. They're a lens. They're a new language that lets us see and describe the invisible flows, the hidden forces, and the dynamic patterns that govern everything from light waves to entire ecosystems. And that leaves you with a final thought. Now that you have this mental toolkit, what happens if you start looking for these patterns everywhere? Where are the sources of change, the points of stability, the cycles of rotation in the systems all around you? The patterns are there, just waiting for you to see them.